Okay, now, with that background material, with the characteristics of the channels, what I'd now like to take a look at will be the actual characteristics of the action potential. Now, this figure here summarizes all the important aspects of a neuron action potential. Now, just to orient everyone to this figure, the dashed lines on this figure represent parameters that are measured in millivolts. So that is the axis on the right side of this page here. This dashed line that is labeled V represents the actual action potential of the neuron. So the line labeled V is the actual action potential of the neuron. Now, in relation to this action potential, we have a dashed line at the top of the figure, which is the sodium equilibrium potential. We also have a dashed line at the bottom of the figure, which is the potassium equilibrium potential. Now, the first aspect I want to consider here is the net force on the ion. Now, this is the resting membrane potential of the neuron, minus 70 millivolts. Now, we said earlier the difference between the resting membrane potential and the ion's equilibrium potential is the net force on the ion. So this resting membrane potential and the potassium equilibrium potential, this distance is the net force on potassium. And we said earlier, it's a very small net force under resting conditions. The difference between the resting membrane potential and the sodium equilibrium potential up here is the net force on sodium. And this is a large distance. Therefore, under resting conditions, we have a very large force on sodium. Now, just going through the action potential to take a look at what is happening to the net force on each ion. Now, these should be your conclusions. When we go from the resting membrane state through depolarization, we are getting closer to sodium equilibrium. Therefore, we're losing a force on sodium. At the peak of the action potential, I said earlier, we are almost at the sodium equilibrium potential, and therefore, at the peak of the action potential, we basically lost our force on sodium. Now, when the cell repolarizes, which is this phase right here, we are moving away from sodium equilibrium, so we're regaining our force on sodium. So just to summarize that then, during the depolarization phase, we are losing our force on sodium. When we get to the peak of the action potential, we have basically no force on sodium. And during repolarization, we regain the force on sodium back to that very high 135 millivolts. Now, we'll do the same thing with potassium. Under resting conditions, we have a small force on potassium. When we go through the depolarization phase, we are getting further away from the potassium equilibrium potential. Therefore, we are increasing the force on potassium. At the peak of the action potential, we are the furthest away from potassium equilibrium, so we have the greatest force on potassium. Now, during repolarization, the membrane potential is getting closer to potassium equilibrium, so we're losing our force on potassium. So just to summarize that again, under resting conditions, we have a very small net force on potassium. During depolarization, the force on potassium is increasing. At the peak of the action potential, we have the greatest force on potassium, and with repolarization, we are losing force of potassium. We're going back to that very small force under resting conditions. Now, on the same time scale then as the voltage changed the action potential, we have the conductance changes to the two ions we're interested in. This solid line here is showing the conductance changes to sodium then. And this refers basically to the opening and closing of the fast channels. Now, just interpreting this in relation to the action potential then. Under resting conditions, the sodium conductance is 0. During depolarization, sodium conductance is progressively increasing. Now, the peak sodium conductance, which is this point here, is the same as the peak of the action potential in time. So peak sodium conductance, this point in time, is the same as the peak of the action potential. That means at the peak of the action potential then, you have the greatest number of open sodium channels. Now with repolarization, you should realize sodium conductance quickly decreases back to that original value close to 0. Now if we take a look at potassium conductance here, under resting conditions, you do have a slight potassium conductance. This is because the ungated channels are open. Now the main point here is depolarization is the signal that causes the voltage-gated potassium channels to open, but they open fairly slowly. So potassium conductance increases slowly during the action potential. Peak potassium conductance does not occur until this point. Now they won't test the exact point, but you should realize peak sodium conductance is during the initial stages of repolarization. So when the cell goes into the repolarization phase, you have a large increase in potassium conductance over resting conditions. Now just to summarize the overall major points here. During the depolarization phase, you have the opening of the fast sodium voltage-gated channels. You have a sodium influx here, and that sodium influx causes depolarization. Now, once you get to the peak of the action potential, you have lots of sodium channels open, but you've lost your net force. And because you've lost your net force, sodium stops flowing, and this is the peak of the action potential. It is not high yield for the exam, but this point here, in the midpoint of depolarization, is where you have the greatest sodium influx. You have lost some of your force, but you have significant number of channels open. At the peak of the action potential, you have the greatest sodium conductance, but you have very little influx because you've lost your force. So this point is the greatest sodium influx, but this point is the greatest sodium conductance. Now with repolarization, all you have to know is you have an elevated potassium conductance, and that elevated potassium conductance causes a massive potassium efflux, and it is the efflux of potassium that causes repolarization. A very important bottom line point is it doesn't matter what action potential you are referring to. All action potentials repolarize due to a potassium efflux. So no matter what action potential you're referring to, it always repolarizes due to a potassium efflux. Now they can ask a few very sophisticated questions here about changes in the channels. For example, they can ask you what would be the consequences for this action potential if you block the opening of the voltage-gated potassium. They can ask you what would be the consequences if you block the opening of the voltage-gated sodium channels. If you block the opening of those channels, you will not have a depolarization phase, and therefore you block the action potential. No other channel can substitute, as we said earlier, in the neuron or skeletal muscle. So blocking the voltage-gated sodium channels then blocks the development of the action potential. Now, another good logical question here would be to ask you the consequences of blocking the opening of the voltage-gated potassium channels. Now, the main point here is, if you block the opening of the voltage-gated potassium channels, you will not block repolarization. Why? Because you still have the ungated potassium channels. So if you block the voltage-gated potassium channels, you will still get an efflux through the ungated channels, but it will be a slower efflux because fewer channels are involved, and therefore repolarization would be slower then. You should understand, if you block the voltage-gated potassium channels, you would have a much slower repolarization. Now, those are all the important details of an action potential. If we go on and take a look at the properties of an action potential, again, we're looking at a neuron or skeletal muscle. The most important property is the refractory period. Now, in step 1, they will only test the absolute refractory period, and they may address it as the absolute refractory period. They can also test it as the functional refractory period. And even if they just ask you refractory period, you assume they're testing the absolute refractory period. They will not test on step 1 the relative refractory period. That is not a point they're interested in testing. Now, with the absolute refractory period, you should realize this is a period in time. The absolute refractory period is a period in time. Now, this period begins at threshold. So the absolute refractory period begins at threshold, and it continues until the cell almost completely repolarizes. So the absolute refractory period continues until the cell almost completely repolarizes. So the absolute refractory period is this period in time. And the absolute refractory period is a period where if you give a second stimulus, nothing happens. So if you give a second stimulus in this period here, nothing happens. You do not get a second action potential. Now, they also expect you to understand the mechanism of the absolute refractory period. The mechanism is the deactivation of the voltage-gated sodium channels. These channels open quickly and they close quickly, and they will not respond to a second stimulus until the cell repolarizes. So the voltage-gated sodium channels will be reactivated in the latter part of the action potential when the membrane potential gets back close to the resting level. They also expect you to know that it is the length of this absolute refractory period that determines the maximum frequency of action potentials you can generate in a neuron. The shorter the absolute refractory period, the higher the frequency you can actually generate, because you cannot generate a second action potential until you get beyond the absolute refractory period. Now, this would be one of the most discriminating questions they could ask in this area. Suppose you block the opening of the voltage-gated potassium channels. If you block the opening of the voltage-gated potassium channels, then you will still repolarize, but repolarization will be slower through the ungated potassium channels. And because repolarization is slower, the absolute refractory period would be longer. So if you block the voltage-gated potassium channels then, you have a slowed repolarization, you only have the ungated channels, and the absolute refractory period is longer, and therefore the maximum frequency of action potentials you can generate would be fewer in that neuron. That would be a very discriminating point to test on step 1. Now the other characteristic that they may test will be factors that affect conduction velocity. Now remember, velocity is speed. It is how fast the action potential is moving down the axon. It is measured in centimeters per second. Now they won't test any details, you just have to know there are 2 main factors that affect velocity. One is cell diameter. The larger the diameter of the neuron, then the faster, the greater the velocity of the action potential. The second factor is the amount of myelin surrounding the axon. The more myelin you have surrounding the axon, the faster the action potential. The bottom line simply is, large myelinated nerve fibers are the fastest conducting nerve fibers, and smaller unmyelinated fibers are very slow conducting nerve fibers. No detail beyond that is important for step 1. Now that finishes off the characteristics of a neuron action potential, and don't forget that also applies to a skeletal muscle action potential. Now chapter 3 here summarizes the important aspects of synaptic transmission. Now if they give you a detailed question about synaptic transmission on the exam, they're almost always going to ask you about neuromuscular transmission. This is the synapse you have to understand in detail. Now what we have here is a figure, and I will go through this figure and highlight the important points in synaptic transmission here. But you have flow statements below this figure, and you should follow me through these flow statements as I go through this figure. Now if this is the neuromuscular junction, you should realize there is no decision making at this synapse. One action potential that comes down the motor neuron, and this is the terminal part of a motor neuron. One action potential coming down this motor neuron should generate one action potential that goes across the surface of the skeletal muscle membrane. So if the neuromuscular junction is working, then normally it's a 1-to-1 relationship. One action potential coming down here will cause one action potential to go across the surface of the skeletal muscle membrane. And this is the cell membrane of the skeletal muscle fiber. Just to orient everyone, this would be the extracellular fluid, and from this point here over to this point here, this would designate the synaptic region. I'm actually moving the arrow here through the synaptic cleft. This would be the intracellular fluid inside that skeletal muscle cell. Now all we're going to do here is to follow the individual events from the time this action potential enters the latter part of the neuron membrane until it produces a new action potential. Now the first important point here is when this action potential terminates on the presynaptic, the motor neuron membrane, all it does is one basic thing. It opens voltage-gated calcium channels in the presynaptic membrane. Now we haven't talked about calcium channels, but if you open a calcium channel, you will always have an influx of calcium ions. So you increase the conductance of this membrane to calcium, that will always cause a calcium influx into the terminal part of the neuron. Now I want to emphasize what we're dealing with here is the influx of extracellular calcium. We are not releasing calcium stored in the terminal part of the neuron. This is free calcium in the extracellular environment that is flowing to the intracellular environment at the terminal part of the neuron. Now, a very big point here is, it is the rise in intracellular free calcium that is actually causing the release of transmitter. Now, at the neuromuscular junction, the transmitter is acetylcholine. Therefore, a rise in free calcium in the terminal part of the neuron is the signal to cause the release of acetylcholine into the synaptic cleft. Just to underscore that point, if I took a micro syringe and injected some free calcium into the terminal part of this neuron, that would automatically cause the release of acetylcholine into the synaptic cleft. All you need is a rise in free calcium to release the transmitter. Now, once this transmitter acetylcholine is released into the synaptic cleft, it will diffuse to the postsynaptic membrane. Now, it is the postsynaptic membrane that has the receptors for acetylcholine. Now, most of the receptors then for a transmitter are on the postsynaptic membrane. I know there can be some on the presynaptic membrane, but the best answer is always the postsynaptic membrane. You should also realize the time taken to release this transmitter and the time required to diffuse to the postsynaptic membrane and attach to the receptor is the largest time component in synaptic transmission. So synaptic delay is mainly due to the time required to release the transmitter and for it diffuse to the postsynaptic membrane. Now, as I said, the postsynaptic membrane has the receptors to the transmitter. And the unique point is these receptors for the transmitter are part of a ligand-gated channel. Now, the postsynaptic membrane, and I want to be real careful here, the postsynaptic membrane here does not have voltage-gated channels. Instead, it has ligand-gated channels. And the receptor here is for the transmitter acetylcholine. So the postsynaptic membrane does not have voltage-gated channels. It has these ligand-gated channels. Now, these ligand-gated channels are regulated by the attachment and then the removal of the transmitter. Now, these are the important characteristics of this specific ligand-gated channel. If there is no acetylcholine attached to this receptor, the lid would be closed then. The channel would be closed. All of these ligand-gated channels would be closed on the postsynaptic membrane. You have to know it is the attachment of the transmitter to the receptor that causes the channel to open. And as long as the transmitter is attached to the receptor, the channel remains open. To close the channel, then, you have to remove the acetylcholine or the transmitter from the receptor or digest it with an enzyme. Now, the next point involves conductance changes to this membrane. When acetylcholine attaches to this receptor, the channel opens and the conductance of this postsynaptic membrane will increase for ions that can diffuse through this channel. Now, it turns out that sodium and potassium can diffuse through this channel. Therefore, the attachment of acetylcholine increases this membrane conductance to both sodium and potassium. But the big point here is, because there's a larger force on sodium, the dominant ion flowing will be sodium and it will be an influx. So because the largest force is on sodium, you mainly have a sodium influx then into the intracellular environment of the skeletal muscle cell. Now this influx of sodium will cause a depolarization. And this depolarization is called an end plate potential. Now this term is location specific. End plate potential refers specifically to the depolarization of the postsynaptic membrane at the neuromuscular junction. Now they wouldn't test details beyond this, but this end plate potential is the amount of depolarization. So if the membrane potential was minus 70 and sodium flows in and makes it go to minus 50, this end plate potential would be 20 millivolts. Now the important point here is, it is this end plate potential, it is this depolarization that triggers the next action potential. You must have a depolarization of the membrane then to trigger the voltage-gated sodium channels. And you should realize, within the synaptic membrane, there are no voltage-gated sodium channels, and therefore you cannot trigger the next action potential within the synaptic region. The voltage-gated sodium channels are not present until you get out of the synaptic region to the free surface of the membrane. So at this point right here, and at the other side, at this point right here, is where you have voltage-gated sodium channels. So it is the depolarization of the membrane at this point that causes the voltage-gated sodium channels to open and the development of a brand new action potential. So just to summarize that then, it is the end plate potential that depolarizes the membrane initially. And that is the trigger for the voltage-gated sodium channels here to quickly open. Sodium flows in here, and you generate an action potential that goes across the surface of the membrane. So that represents all the details of synaptic transmission at the neuromuscular junction. Now the next page here simply summarizes some additional details about the synthesis and the removal of acetylcholine. Now again, this is not real high-yield information. You only have to know the main points here. The first point is acetylcholine is synthesized in the motor neuron terminal. You use acetyl-CoA as a substrate and choline, and what catalyzes this synthesis is choline acetyltransferase. So acetylcholine is synthesized in the nerve terminal. Now once it is synthesized, it is packaged in vesicles and released in a quantal manner into the synaptic cleft. Now as we said earlier, this acetylcholine will attach to ligand-dependent channels on the postsynaptic membrane, and as long as the acetylcholine is attached then, the channel is open. Now the very big point about this figure is the action of acetylcholine is terminated mainly by enzymatic destruction, and this is via acetylcholine esterase then. So this is via acetylcholine esterase. I want to emphasize that the main mechanism terminating acetylcholine action is enzymatic by digestion with this enzyme. And this enzyme will release acetate and choline. And the final point here is the choline is taken up by the nerve ending and recycled then. Now this scheme is compared with the scheme for adrenergic transmission then. Now there's some real differences here. This is the terminal part of a neuron that releases norepinephrine as a transmitter. Now the basic substrate for the synthesis of norepinephrine is tyrosine. Now, the nerve terminal does not manufacture the tyrosine. It is taken up by the cell. So this substrate is taken up by the cell. The first two steps in the synthesis will occur in the cytoplasm, and the main limiting step here, the main rate limiting step, is the first step, which is catalyzed by tyrosine hydroxylase, which converts tyrosine to dopa. Now, once you form the dopamine, then it is taken up into a vesicle, and it's in the vesicle where you have the final synthesis of norepinephrine. Now, this norepinephrine can be slowly released through this membrane and be digested by MAO that would deactivate the norepinephrine. But most of it will be released into the synaptic cleft. It goes to the postsynaptic membrane and attaches to receptors on the membrane. Now, the big point here is, with catecholamines at adrenergic synapses then, you do not have an enzyme to terminate transmitter action. You should realize other processes are involved. You can have diffusion away from the receptor, which is one mechanism to terminate action, but you should realize here that reuptake of the norepinephrine by the nerve terminal is a major mechanism of terminating norepinephrine activity. So just to repeat that, the major mechanism of terminating the activity of norepinephrine is the reuptake of the norepinephrine into the nerve terminal. There is no major enzymatic destruction of the norepinephrine. Now, finally on this figure, don't forget that norepinephrine is not the endpoint in the adrenal medulla. The adrenal medulla will convert norepinephrine into epinephrine, and this is a hormone released by the adrenal medulla. Now, on the next page here, we have a diagram of a neuron, and we have to say a few things about synapses between neurons. Now, this is a diagram showing an entire neuron. This represents the cell body and the dendrites. This is the axon of the neuron, and this represents the terminal parts of the neuron, and this would be vesicles of transmitter. Now, the first aspect I want to address here is the location of the channels. Now, in the cell body and on the dendrites is where you have all of the synapses. And therefore, on the cell body and on the dendrites, you have mainly ligand-gated channels that respond to the different transmitters. So just to repeat that then, on the cell body membrane and on the dendritic membranes, you have mainly ligand-gated channels because these channels are required to respond to the various transmitters released. The cell body and the dendrites do not have a high density of voltage-gated sodium channels. Now, to initiate an action potential, you need a fairly high concentration of voltage-gated channels. And they begin at the axon hillock or the initial segment. So in this region here, you have a much higher concentration of voltage-gated sodium channels than you have on the cell body and the dendrites. Therefore, then, the local potential changes that are generated in the cell body and on the dendrites must flow to the axon hillock or the initial segment, and if you depolarize this membrane far enough, you activate enough voltage-gated channels, and that initiates the action potential. And the axon is characterized as having no ligand or very few ligand-gated channels. The axon itself has mainly voltage-gated channels. Now, when this action potential gets to the terminal part of the neuron, we have a situation similar to the neuromuscular junction. You allow calcium to come in here. The increase in free calcium releases the transmitter that may or may not generate an action potential in the next cell. Now, I want to focus on the different types of synapses that you can have on this cell body membrane or on the dendrites. And we'll classify these into two basic categories. Suppose we just pick one synapse here, and we'll say at this synapse we release a transmitter that causes a depolarization of the postsynaptic membrane. And if this transmitter causes a depolarization of the postsynaptic membrane, it generates, as shown on the next page, something called an EPSP. Now, an EPSP is an excitatory postsynaptic potential. This is excitatory because it is a depolarization. You're moving towards threshold, therefore you are exciting this cell. It is excitatory, as I said, because you're moving towards threshold. Now, the mechanism that generates an EPSP, we can assume it is due to an increase in the conductance to sodium and potassium. In other words, the mechanism that generates an EPSP is more or less identical that generates an end plate potential. These two terms are location specific. End plate potential is the depolarization at the neuromuscular junction. EPSP is the depolarization at a synapse between neurons. They both increase sodium conductance. They both cause an influx of sodium, and it's the influx of sodium that causes the depolarization. Now, at other synapses, we will release different transmitters. And suppose another transmitter does not depolarize the postsynaptic membrane, but instead hyperpolarizes the membrane. If it hyperpolarizes the membrane, then it's called an IPSP. An IPSP is an inhibitory postsynaptic potential. It is, as I said, a hyperpolarization of the membrane. It is considered inhibitory because the membrane potential moves further away from threshold. A hyperpolarization moves the cell away from threshold. It is less likely to be excited. Now, you should realize an IPSP can never be produced by opening sodium channels. It must open a channel that causes a hyperpolarization. Now, in a few instances, it has been demonstrated that an IPSP is produced because of an increase in the conductance to chloride. Now, this means not all cells are in equilibrium with chloride. These nerve terminals are not at equilibrium with chloride. Therefore, when you open up chloride channels, we know chloride flows to hyperpolarize the cell. Now, you could even figure out which way the chloride would probably flow. It must really flow into the cell. A negative ion, like chloride flowing into the cell, will produce a hyperpolarization. And that is the mechanism of an IPSP they're most likely to test on step 1. You might also want to remember an IPSP can also be produced by an increased potassium conductance. Because potassium is not quite at equilibrium, if you open more potassium channels, you'll get a greater efflux of potassium and the cell will slightly hyperpolarize. So you should have a general idea about the characteristics of an EPSP versus an IPSP produced on the dendritic membranes and the cell body. Now finally, right here, related to this material, boards can compare a chemical synapse with an electrical synapse. Now, what we have been talking about so far are chemical synapses. Most synapses in the mammalian nervous system are chemical synapses. There are very few electrical synapses in the mammalian nervous system. However, they do exist, and they're present in invertebrates. Now, if they do exist, you should realize the action potential across electrical synapses is due to the direct flow of current. There is no chemical intermediary here. It is a direct flow of current. Now, an electrical synapse can conduct in both directions, and there's essentially no delay. Now, this is very different with a chemical synapse then. An electrical synapse, then, they work in both directions, and there is no delay basically at all. Now, electrical synapses are basically similar to gap junctions. Gap junctions are just regions of low electrical resistance that connect cells basically electrically. So electrical synapses are caused by the direct flow of current from cell to cell through structures very similar to gap junctions. Now, we'll talk about this later, but gap junctions are present on cardiac muscle cells and smooth muscle cells. And therefore, these cells are connected electrically, and the action potential can flow from cell to cell. Now, Bohr's can have a very unique way of testing your understanding of electrical versus chemical synapses by creating a specific artificial situation. Suppose we go back to this neuron here, and suppose we attach electrodes at the center part of this neuron. Now, if I place these artificial electrodes at the central part of this neuron and I depolarize the axon to threshold, if I depolarize the threshold at this point here, I generate an action potential that goes downstream to the terminal part of the neuron. I will also generate an action potential that goes upstream towards the cell body. You should realize the velocity of these two action potentials will be the same, because downstream and upstream, the axon has the same diameter and the same amount of myelin. So the velocity downstream is the same as the one upstream. Now, the one going downstream is the natural direction of the action potential. So this one going downstream will release transmitter. And this transmitter will potentially produce another action potential in the next neuron. However, the action potential going upstream towards the cell body will never release transmitter. This is the non-natural route of an action potential. The action potential will enter the cell body, and the big point is it simply disappears when you run out of voltage-gated sodium channels. So once you enter the cell body, the density of voltage-gated sodium channels diminishes, and at some point that action potential simply disappears. It never releases transmitter. Now, that's a unique way of testing chemical versus electrical synapses by just going over some basic characteristics of the chemical synapse. Now, at the end of this section, we have some additional information to summarize the basic important transmitters. Now, we've already talked about acetylcholine as being a major transmitter, and you should be aware acetylcholine does act as a transmitter, but I want to emphasize here it is the enzymatic destruction of this transmitter that is the main factor that is terminating transmitter action. This is the only major transmitter where an enzyme is utilized to terminate transmitter action as the major mechanism. Now, another transmitter group will be the biogenic amines, and these will be present at many synapses in the peripheral and the central nervous system. I want to point out here that the main mechanism of these transmitters terminating action is reuptake by the presynaptic membrane, as we stated earlier. Now, there are other transmitters in the central nervous system, and you should realize amino acids are also transmitters. And you should memorize that both glycine and GABA aminobutyric acid, are inhibitory transmitters in the central nervous system. Both of these amino acids will generate iPSPs via opening ligand-gated channels. Now, two other amino acids you'd be aware of are glutamine and aspartate. And these are basically excitatory transmitters. These transmitters will open sodium channels and create EPSPs then. They stimulate or are considered excitatory. Now, another point that they may test here is that non-peptide transmitters are basically synthesized in nerve terminals. Earlier, we went through the steps in the synthesis of acetylcholine and norepinephrine. Acetylcholine and norepinephrine are synthesized in nerve terminals. But with amino acid transmitters, they are synthesized in the neuron cell body. So it's in the neuron cell body that synthesizes these amino acids. Once they are synthesized, they're packaged in vesicles, they're transported down the axon, then they are stored and released from the nerve terminals. The bottom line point is, the amino acids are synthesized in the cell body of the neuron, but they are stored and released from the nerve terminals. Now, just like catecholamines, you do not use enzymatic destruction as a major mechanism of terminating activity. It is mainly reuptake by the presynaptic membrane that terminates activity. Now, another transmitter that's not too important for our purposes is nitric oxide. Now, nitric oxide is a lipid-soluble transmitter. Therefore, it cannot be stored in vesicles. If you try to store a lipid-soluble substance in a vesicle, it simply diffuses across that membrane and will dissipate very quickly. So nitric oxide is a lipid-soluble transmitter. It is synthesized as it is needed. The big point here, it is synthesized as it is needed, and it is also an inhibitory transmitter in the central nervous system and the enteric nervous system. There's a few other substances that are released at synapses that are not transmitters. These are called neuromodulators. Now, as I said, they are not transmitters. They function by altering the sensitivity of the synaptic membranes. So they alter the effect of the transmitter on the postsynaptic membrane, and therefore they alter the activity of the synaptic membrane. Now, these neuromodulators are frequently peptides released by the neurons, and a very small point is they do act at very low concentrations, but they generally have a long duration of activity. Now, finally here, we do have to say a few things about presynaptic inhibition then. Not a real important topic, but worth mentioning. Now, some inhibitory neurons can form collaterals that will synapse near the terminals of an excitatory action. Now, these collaterals almost always interfere with calcium influx. And therefore, because they generally diminish the calcium influx, they decrease the ability of this synapse to release transmitter. Now, we know a transmitter at one of these collaterals is GABA, so GABA does function as an inhibitory transmitter here. You might also want to be aware of the fact that at the presynaptic membrane, at adrenergic synapses, you can have alpha-2 receptors, and the transmitter norepinephrine can act presynaptically on these alpha-2 receptors to inhibit synaptic transmission. This terminates this section then. As I said, this is not a super high-yield topic for Step 1, but there are basic questions in this area that they test, And if you understand this material, other areas of physiology are more meaningful, and there is some spin-off to pharmacology.